Hello, this is the first video of a Hyperbolic Functions 1 series and introduces the definitions and graphs for hyperbolic functions. The curve formed by a heavy chain hanging under its own weight looks like it might be parabolic, but it's not. It's called a catenary curve. The simplest shape of this form is described by the function y equals a half e to the x plus e to the minus x. The functions sine theta and cos theta are sometimes referred to as circular trigonometric functions, because if we plot x equals sine theta and y equals cos theta as theta varies, we get a circle. So we have it's theta. And we'd also find that x squared plus y squared would equal 1, for example here with radius 1, the unit circle. If we plot x equals sin t and y equals cos t, as t varies, we get one branch of a rectangular hyperbola. Note that t does not relate to an angle, and that we would have x squared minus y squared equals 1. Note that the branch of the rectangular hyperbola is when x is positive. This may not mean very much to you at the moment, but this is where the hyperbolic functions gain their name from. We define cos x to be a half e to the x plus e to the minus x. If we were to draw the graph of y equals e to the x, it looks like this. If we then can think about the graph of y equals e to the minus x, we see the red curve here, and the graph for y equals cos x lies midway between e to the x and e to the minus x. You'll note that the minimum point of this graph is 0, 1. But the range is therefore y greater than or equal to 1, and that the domain is x is in the real values. As x turns to infinity, cos of x will also tend to infinity, and as x tends to minus infinity, the same is true, the graph being symmetrical. For the function sin x, the definition is that it is half of e to the x minus e to the minus x. So where it differs from cos x is in the sign here. Again, building the graphs, we look at y equals e to the x and y equals minus e to the minus x. Then we can see that the graph of y equals sin x would lie midway between. It passes through the origin, which is a non-stationary point of inflection. We can see that the domain is x is real, and that the range is also that y is real, with no restrictions. As x tends to infinity, sin x tends to infinity, and as it becomes large in a negative sense, then sin x tends to minus infinity. So, considering further the properties of hyperbolic functions, first we'll look at cos x. We can see that it is a symmetrical graph in the line x equals 0, and therefore that cos of minus x equal to a half e to the minus x plus e to the x is the same as cos x. Therefore it is what we call an even function. In contrast, sinh of x has rotational symmetry, and sinh of minus x which will equal half of e to the minus x minus e to the x is equal to minus sinh of x. It is therefore an odd function. You may note the similarities with the circular trigonometric functions cos x and sin x. If we add the two functions, using their definitions, we would have half of e to the x minus e to the minus x plus half e to the x plus e to the minus x. And thus we can see that the e to the minus x will cancel each other out, and we would just end up with a half of 2 e to the x, in other words, e to the x. Let us now consider y equals tan x, where we have that tan x equals sin x over cos x, which, were we to use their definitions, would be half of e to the x minus e to the minus x over half of e to the x plus e to the minus x. If we multiply up through by 2 and then by e to the minus x, this would give us 1 minus e to the minus 2x over 1 plus e to the minus 2x. Let us now consider the graphs. Here we have y equals cos x in green and y equals sin x in the orange. Considering then for positive x, the cos x and sin x values are very similar, and therefore it looks like tan x will be around the value of 1. However, if you look at the negative values of x, you can see that they are the negative of each other, and therefore it is likely that tan x approaches the value of minus 1. If we were to plot these values, this indeed would be the case, and there are asymptotes at y equals minus 1 and y equals 1. As x tends to infinity, y tends to 1, and as x tends to minus infinity, y tends to minus 1. To summarise then, the range and domain for each of these three hyperbolic functions. For cos x, the domain is that x is in R and y is greater than or equal to 1. For sin x, both the domain and range are simply that x and y lie in R respectively. For tan x, the domain is that x is in R, but that y must lie between minus 1 and 1. In the next video, we will solve simple equations using hyperbolic functions.